Well, this is a can of some really nice flux. This is a syringe. Same flux in the syringe as in the can. This is a soldering iron. This is smoke. It does smell very, very tasty. I really like the smell of the smoke. However, I am told that the smoke might be not so good, let's say. And so to that end, at some point, I have acquired that. It comes with a juice cord, which, if plugged in, turns it on. Really, all it is just a simple fan with a filter. And it creates enough air to suck up all the smoke and put it through the filter, and I don't get to enjoy my smoke anymore. And at the same time, presumably, I'll stay alive a little longer. However, when I am in the midst of doing something fun, what I tend to not do is turn it on. I don't know why. I mean, it's right here. This hand can go reach it, turn it on. This hand can go take the soldering iron and do stuff and then turn it off. And yet I don't do it. Don't ask me why. So I figured that maybe, well, I'm gonna make it automatic. Now, this soldering iron right here has this stand. Look at this action. I pick up the soldering iron, this goes up, put the soldering iron back in, it goes down. And you hear the clicking? What this does is it tells the base station of the soldering iron that the iron's in the thing, and it will turn down the soldering iron's temperature so that the soldering iron doesn't burn out, or rather burn up the tip. And the way it's done is this wiggles, and in the back, in here, there's a micro switch and a little 3mm jack. Actually, no, sorry, let's be proper, not communist. A proper would be what, 1/8? 1/8 of an inch jack. In fact, it's right here. It goes into the base station. You know, switch close, switch open, switch close, switch open. So I figured, why don't I do the same thing? Why don't I need some light here. Add another switch right there. Little Omron. Oh, this is going to turn into a disaster pretty quickly. Little Omron. I'm pushing up and down, and it's not focusing, of course, because it wants to look at the 3mm jack. Little tiny little Omron switch. And all the switch does, it flops and flips and flops and flips. And I got my own 3mm jack. Excuse me. 1/8 of an inch jack. Hooked up. So now I can know if I have a soldering iron in the thing, or if the soldering iron is out of the thing. this might start getting us somewhere. Now I need to get the phone hooked up back so that it's nice and even over my notepad and doesn't droop. Is it drooping? Yeah, I think that's fine. So what we got right now is, well, we got ourselves a switch, right? So we got a T, right? Let's call this an off position. So switch is going to be in this position when we're off, and when we pick up the soldering iron, it's going to move to the other position, and it's going to be on. Now, one way this can be done is, well, using my favorite electromechanical device, also known as a relay. We would take that wire, this will be ground, this will do nothing, and then this is the switch terminals, just map 1 to 1. And over here, we're gonna have a, what am I doing? Yes, so we're gonna have plus some volts. This is gonna go to a coil. This is gonna go to ground, right? And we're gonna have a relay, what, double pole rather. Sure, why not, right? And our power input's gonna come here, and this is gonna be our little fan thingy, right? However, this is very immediate, right? Like pull the iron out, turn the fan on, put it back in, turn it off. Yeah, I mean, come on, too simple, right? You have to make it more complicated. What I wanted to do was to, if I just pulled the iron out and decided not to solder, then if I stick it back in quickly, nothing happens. And so time delay on start. And the other way, time delay on stop as well, right? So I put the iron in, and there's like a second maybe while for the fan to still run so that, it sucks out the rest of the smoke or whatever, something like that. Oh, and I wanted them adjustable. So I know nothing, okay? I'm not an expert. I mean, all right, so let's do this very, very simply, okay? So let's say, ground is assumed, okay? So like, I'm not gonna draw grounds over here. So let's assume that I want, oh, I don't know, this is my output, right? I want 12 volts in here, but I want to I want to put a time delay on that. Okay, so here's my switch, here's my plus 12 volts coming in, that's my output. So I'm gonna put a switch in here, obviously, but if I connect it straight, there's no delay. So what we do is we slow it down. How do we slow it down? Okay. So in order to slow it down, we basically need, once the juice starts flowing in, we need to soak up some of that juice into something else. And we need to do that for a certain period of time. Oh, wait. Juice soak up devices. I think they're called capacitors. So if we stick a cap in here, sufficiently large, right? This thing, again, right? So this is my load. Here, mysterious load, right? There's, my ground, obviously, right? Again. Okay, so this is no better. Actually, this is worse, because what's going to happen is this guy is going to soak up a lot of juice very, very quickly, overload the power supply over there for that short period of time it takes for the thing to charge. Aha, but what if we slow it down? Right? Right? I mean, come on, guys, right? Like, everybody knows this. It's a time delay circuit. So now this resistor is slowing down the flow of current, and current is what causes capacitor to come up on voltage. And so in fact, the time it's going to take the capacitor to come up to 60%, oh wait, no, excuse me, 66.666, I think, if I remember right, 2/3 of the supplied voltage is going to be, just don't forget to convert everything to straight units. So microfarads should be converted to farads, and kilo ohms should be converted to ohms. But anyway, and it's in seconds. And if I remember my books right, this is called a time constant. Anyway, so this is all good. So, well, okay, fine. So let's put our load in here. That's our fan. Are we done? Well, not really. Okay, maybe on a turn-on side of things we're done. Maybe, because what has to happen now is you have to account for, all right, so if my load, actually, no, excuse me, my load in this particular case is not a fan, obviously it's a relay, right? It's the relay that turns on the fan. Where is it? It's this guy. But anyway, so let's say relay is at 12 volts, and I'm giving it 12 volts over here, but it's going to draw 6 milliamps, portion of which is going to be dropped over the resistor. So really we need to go higher than 12 volts, and it's just messy. Probably for a reasonable size time delay. I didn't even do this way, but I'm just guessing, right? It's like you'd need the pretty decent size cap. And most importantly, this doesn't solve the off equation, right? Because when I disconnect this, the cap's gonna have some juice in it, right? And it's gonna feed it, but cap's gonna get discharged super quickly. There's no way I can stick a second resistor anywhere in here to slow down the cap. Well, no, I guess I could, right? Like we could stick a second resistor in here. That will slow down cap's discharge, but imagine you're running a relay off of the cap, and if you want to run it for 3 seconds, I mean, come on, right? Like, okay, fine, this does take, it's the relays I use, right? 60 milliamps. But, so, no, what you want, I don't know, I kind of, again, I'm not an expert. I've mucked around with similar circuits. My impression is this, right? So you want your magic box that controls stuff to basically be infinite input impedance. In other words, because look, this guy, I mean, very, very, very simply, right? Like this load, its impedance, its like its resistance, its impedance is very, very low. Relatively speaking, it's so low that it's going to draw 60 milliamps of current. You want to draw like nanoamps of current. Like basically, you want your resistance to be like infinite, virtually, because then you're not causing any issues upstream, right? That's the standard quote-unquote voltage sag problem, whatnot. And you want ideally the output of the circuit to be zero resistance. Right? So that it is not affecting anything downstream. It's a standard like input impedance problem, input output impedance problem of any circuit. Beyond the scope of this. But anyway, so I kind of came across this realization very quickly. So I need some magic box that on the input will take my, time delayed on off type signal, not soak up too much of it, so that the capacitor can discharge normally in a fine manner and not super quickly, and I wouldn't need like super big cap over here, and give me enough, or rather low enough output impedance so that I can actually run a relay off of it. Okay, so this is probably way too messy. So, to our friend Google. And what I found was a fanciful 555 timer. Now, I have to tell you, the timers I used, the typical implementation of it is this. I did not use this. It does not work. I will tell you why. For me, I will tell you why in a minute. And probably the reason why it doesn't work is because I'm abusing it, or rather I'm misusing it. because I'm totally not doing what it's supposed to do. What I used was I believe it's called, I'm looking for my parts back. Yeah, it's a TLC 555. And again, from what I understand, the types of transistors used in these implementations is different. This is implemented using, oh God, I think it's using CMOS versus, forget what's in there. Anyway, at any rate, this works, right, in my application. So here's, you can, there's a whole bunch of stuff on 555 timers, and usually people use them to like flash an LED on and off for a certain time, or like you push a button, let it go, and something lights up for a given period of time and then shuts down. So let's draw, you know what, let's do this. That's the doodad. That's one of these timers. So it's a little bug with 8 legs, right? Okay, so like the dot is here, right? And this is pin 1, 2, 3, 4, 5, 6, 7, 8. So the first pin is ground. The second pin is called trigger. Third pin is output. Fourth pin is reset. Fifth pin is control. Sixth pin is threshold. Next one over is discharge. The next one over is V plus. Okay, so V plus and ground, obviously, right? The only thing that these guys want you to do is they want you to grab your power supply. I used a 12-volt relay. Man, this thing's focusing on my hands, huh? Wow. Ground, trigger, output, reset, control, threshold, discharge, positive. So you take your positive, supply, and they want you to, it's in the data sheets, they want you to put a couple of caps in here. One of them is an electrolytic 1 micro, and this one is a ceramic 0.1, right? And they just want you to decouple them to ground, right? And we're done with power, basically. Okay, so output is the thing that's outputting, and trigger, reset, and threshold is how you control it. So if reset goes low, the thing goes low. If reset is high, it's out of the picture. So we're not going to use reset. So I'm going to just go and make reset high. Okay, so not using reset. Now, the other thing is this. So output is obviously my output, right? And output is going to be connected to my relay, right? So this is my relay coil. Now, the question is, what's on the other side of the relay coil? Because this output of the 555 timer, it can go either high or low, depending on what you do with controls. And you can source, meaning, basically output is high, you're on, and output's low, grounded, you're off. Or you can sync, meaning that you put your power supply over here, and then if the output's high, nothing's happening. But if the output is low, it acts as a ground and your device works. So it's sourcing versus syncing, right? We're kind of sourcing power from it, we're syncing power into it. What I found was, and it's in the data sheet, you can source like, I don't remember what the number is, but it's not enough. It's like, I want to say 10 milliamps. I'm not sure I remember it right, but anyway, you can source a lot less than you can sink. Also, if you're sourcing, it's kind of going to work ass backwards, just logically. So I stuck on sinking, which means that essentially output's my ground. So if one output's high, I'm off. When output's low, I'm on. And this is running off of my power. Okay? So it's a relay coil, right? It's an inductor, right? So when we're going to switch it off, we need a flyback preventer. Or is it a flyback diode, rather? Again, look it up, inductors and flyback diodes if you don't know what that is, right? So this is positive side here, so that's our flyback diode. Basically, when you disconnect the power rate, there's still juice stored in the inductor. It wants to go somewhere, and if this was a regular switch, it would just make a spark in a switch. But this is all logic. This is all, well, it's not logic per se, right? But it's all transistors, and so that quote-unquote spark on the scope, it looks like I forget what it was. I did it in a simulator. I didn't even put it on a real scope. It's like a kilovolt or something stupid like that. Just a massive spike for like very short period of time. It's a huge spike of voltage. It's gonna zap this, right? So we don't want that. So what we do is once we disconnect this, oh yeah, and it goes backwards, right? So this is why this is positive, so it can't go here. Diode prevents that. But when we disconnect, it actually does want to go here. It's backwards. So it just spins internally and just dissipates. Classic problem of DC inductors. Anyway, so flyback diode. And okay, so the only thing that's left is our controls. So here's the moment where I start misusing it. I put my threshold to 12 volts. Okay, so basically threshold's not doing anything at this point. And, or rather, no, I'm sorry. So threshold is actually doing something. Threshold is essentially forcing this thing to go, I believe, low in this particular condition. And trigger is what I'm going to hook up to my switch, right? Now, so for now, I'm going to draw it with no resistors. So this is my 12 volt rail, right? When a switch hooks up to on, it puts 12 volts on trigger. Now 555 timer works like this. If trigger's high, the thing turns off because threshold's high. But if trigger's low, it's going to turn on. So we ground this guy. I'm running out of space over here, am I not? So I'm just going to do it like this. Okay. No frills. Basic so far. Look, so right now we are, the trigger is grounded. Okay. In that spec for TLC 555, it says the trigger takes precedence of everything. Meaning, if trigger's low, the darn thing's on, no matter what the other inputs are, besides from reset, of course. But we reset, we're not touching it. Which means this is high, plus 12 volts, because that's what we're supplying here, which means that this thing's doing nothing here, right? Now, we'll flip the switch over here. This goes to 12 volts. Threshold being 12 volts now causes the timer to switch off. This goes low, and all of a sudden, everything lines up, and our current is flowing. and the relay turns on. I mean, I didn't draw, you know, like here's my contacts, right? That, but you get the idea. So, but this is not time delayed, right? So far, it's just a weird on and off switch done through a $1 part for no reason. I mean, why? But we forgot our magic. So slow down the thing. Let's slow down the thing. So in order to slow down the thing, remember, we have to put a cap in here. Okay, so we're going to put a cap. And obviously, since, you know, this is going to be grounded, right? And to slow down charging of the cap, I can put a resistor on this line, but no, I want to control my off time delay and on time delay separately. So now it becomes very, very easy, right? I put a resistor in here. And however big this resistance is, the bigger this is, the slower the cap will be charging. The slower the threshold will see the voltage high enough to react to it. Sorry, trigger, excuse me. The slower the thing will be. The smaller the resistance, the faster the thing will be. And it's the same thing on the discharge side. Put the resistance in here, right? Now this is all fixed. How do we make it adjustable? Well, I'm glad you asked. Right? And that's your adjustment. If I use LM555, which by the way can handle more current, although this can handle my 100 milliamp. This guy on the sinking side, when I'm passing current through it when I'm low, which is what I'm doing, can handle 100. My relay and my indicator is together about 60, so I'm like half capacity here. But if I need more current, LM555 has current, more current, which I promised to tell you why this wouldn't work. The reason why this didn't work for me in LM555, which I bought, which I tried, which I had, was because data sheets at least are slightly different. Here, trigger is explicitly, in this timer, the one I used in TLC 555, the trigger explicitly, the data sheet explicitly states that if trigger is being manipulated, it takes precedence. If trigger is low, no matter what threshold is, the thing is going to go high. Trigger low causes the timer to turn on. In the other data sheet, it goes like this. Low pulse on the trigger input causes it to turn on, and then threshold causes it to turn off, and the pulse on reset causes it to turn off as well. And when I tried LM555 in this scheme, it did not work. And so for what it's worth, right? This works. Also, I could not find an implementation of what I needed, which was one timer, independent control of on and off delays using a switch, right? You see how we're constantly engaged here and constantly engaged here, right? It's not a push button. It's not a single like little boink, right? It's going to stay there until it changes its state. And so this is maybe why I made this video. It's because maybe it's going to have the same, somebody's going to have the same problem. So this is that scheme implemented. So I need to put some values in here. So I'm running an Omron little relay here. It's a 12-volt relay that can control up to 5 amps. Believe it or not, I don't believe that it can do 5 amps at 250 volts, but the datasheet says so. Contacts on it are tiny. That's what bothers me, right? My flyback diode is right there, hiding in there. I don't know if you can see it. It's behind the LED. The LED runs in parallel with the diode. It's just an indicator because, you know, I think it's the third law of electronics that says every contraption must have indicators. That right there is the timer. The cap, okay, yeah, so I was going to put some values on this. So the cap I used in the discharge circuit, and I just experimentally plugged in different caps until I got to the, obviously you can change all this around, bigger cap, small resistor, bigger cap, bigger resistor, smaller cap, or whatnot. I used 47 microfarads over here, electrolytic, obviously properly polarized. Your positive is going to be right here, right? And I used 100K pots here, although the on pot, this guy, there's a, wait, did I use 100K on that one? I don't think so, actually. Yeah, I'm using, I just checked, I have another note that's sitting out of view that I'm checking with. This cap, sorry, this is a 200K. So this was a 200K, this was a 100K. And in series with it, I added another 100K trimmer on board in the final implementation so that I can like, trim the range, because I just wanted to have that option in case I wanted to tweak it, and so I didn't have to resolder anything. Anyway, I mean, again, experimental. You can figure out these using circuit simulator or just build it and play with it like I did. Okay. So these are power capacitors. These are two power supplying capacitors. That little capacitor, that data sheet tells you it's this little guy in the back right there. It's this one is decoupling. I didn't draw it here yet. It's basically decoupling this control pin. So yeah, you can read the data sheets or like look at other stuff about TLC 555 timers. They tell you what the pin does, but basically if you're not using it, you're supposed to, you know, do that, because otherwise it can pick up crap from the air, you know, all sorts of wavy, interferency, you know, type stuff, and it's gonna mess with the internal brain box, or not brain box, but internal thresholds of the 555. So that's that decoupling cap. These are my two trim pots, and this is my switch simulator, right? So it has two positions, one position, the other position. Oh, and I forgot to turn off my goddamn power supply. So you get to, it actually did work already. Look, so delay on, delay off, and I can control it, right? So if I roll this pot, this is an off pot. Roll it a little higher, right? So this is, oh sorry, this is an on pot. On pot? Yes. So I roll it a little higher. It's gonna take longer to turn on. Did I roll it too high? I probably, yeah, see how long it took? I can, and then this guy, let's say I roll it all the way down to nothing, and that will turn off very quickly. See, instantaneous turn off. Turn that, this is an off pot again, I'm tweaking here. Turn that on. I'm gonna tweak that down so we don't have to wait. Yeah, it took a little longer to turn off. So the best way to look at it is by using this. So I'm gonna look at the voltage that my threshold pin, excuse me, that my trigger pin sees, right? My trigger pin is the one that I use to control the whole shebang. So this is an analog meter, right? It's set 2 volts. And I'm looking at the voltage over there. My voltage at which it will turn on and off is going to be 4. We read it on DC scale, so about 4 is like right about here. And so watch the needle. This is why I love analog meters. Click. And then it continues charging to 12 volts, obviously, the capacitor, right? But the thing turns on when it's 4. Pew! Click! Ah, I can watch this all day. Seriously. Pew! Pew! That was, I decreased the delay. All right, so I'm just playing with pots here. Pew! Click! Pew, click. I don't know if you can hear the relay clicking or not, but it is. So there you go. That's the prototype. That's the actual implementation. So let's see here. How do I show this to you? So input power, main power switch. By the way, I should not be doing this with a metal screwdriver, but I know it's powered off. Input power switch. This is the relay. I use the socket so that in case the relay goes, I can replace it. This is a power supply which takes in, you know, my standard wall 125 and makes 12 volts out of it. I really like these little things. They're tiny. They're super reliable. I think they're medical grade even, maybe. I get them on Mauser. It's XP power. They have, let's see, what does it say? It says output 12 volts. Yeah, half an amp at 12 volts, guys. Seriously, 0.41 amp. Do you see that on the little label? I really like these. Maybe they're a little pricey, but anyway, so the big power wires that are going to be switched on and off by the relay are on the bottom of the board. The flyback diode is on the bottom of the board. Right, and then so yeah, there's input power to the relay, output power off of the relay. Sorry, well, input power to be switched into the relay, output that goes in here. This is an RC unit. So inductive load in DC, you do that with a flyback diode. Inductive load in AC, one of the ways of protecting, same problem, right? One of the ways of protecting against that is using an RC unit, which is basically a cap and a resistor. This is a really nice single box solution. Why? Because the fan is inductive. Technically, it's a motor, right? So it's an inductor. It has a coil in it. I don't know if that would have been a problem or not, because the relay itself has an inductive rating, and I'm assuming that does not assume having an RC snubber. These are called RC snubbers, by the way. RC snubber, yeah, maybe. Not a freaking expert. I'll add it. I added it as an abundance of caution. Why the hell not? Leave me alone. Anyway, so power comes off of this, and then this is my actual board, right? So timer, that's the timing capacitor. These are power decoupling capacitors. That's that control decoupling capacitor. That's that adjustable resistor that goes in series with my on delay resistor. Off delay resistor. The board is, it's gonna, just the way this chip is laid out is a lot easier to lay out the board backwards. So this is positive and this is negative. And also this is a really nice Adafruit. It's like proto board that you solder, but I don't use like plus minus. Instead I used that whole side for negative and this whole side for positive. This is why I scraped off. You see, this is just the minus and just the plus scraped off the other. That's really it. And of course, mandatory indicators. By the way, the actual rule is your indicators ideally should be those old school Fender style jeweled little bulbs, you know, that use proper incandescent light bulbs in there. But in particular, that's a pretty big holder. I was trying to, you know, fit in the case, so I have an excuse. I used an LED because of that big case problem. My two on delay and off delay adjusters, right? And it works just like a pass through. There's 1 amp fuse in there. Man, this is the first time I'm using a Pixel phone instead of an iPhone, and this thing cannot focus. Like, damn serious. Input. This is output, and this is my 3mm jack, which is going to connect to the other 3mm jack. Right, this is the switch. Right, so this is the actual diagram that I drew when I built it. This is a lot cleaner than what I drew just now on paper. It's exactly the same diagram, but it also shows the switch and my diode and the relay and whatnot. Okay. Well, and I guess, how should we do this? One-handed, as always, yes. Where's my power cord? Now I'll put this down. I don't need 2 hands. Sorry. Well, maybe you'll see me fumbling around over here. So this is power in. There's another power cord here somewhere there. So this is going to be output. Okay, so connected my input power, connected my this goes to the fan. Power on. This switch, it's a switch that controls manual auto, right? So I go to manual mode. Oh yeah, that needs to, right? So I go to manual mode, it's just on. And this is automatic mode, which will use the timer logic and the time delays. So I need to connect my, because the switch is in here, right? So I need to connect, because the box is gonna live like right there, over there, right? And this lives in here, so I need to connect them. That's why the whole jack business. And besides, so that I can move stuff around independently. Okay, don't get zapped. There we go. So now, see, because the iron's not on it, I thought it was not on it, and turned the fan on. Okay, so I'm gonna pretend the iron's in, and the fan comes off. Iron off. Oh yeah, the other cool thing about this is because it's time delayed, so if I put the iron in and pull it away very quickly, right, I decide I'm not done and I'm gonna solder again, it's not gonna keep power cycling the fan, right? See? Yeah, that one did. But, you get the idea. And I can adjust that off delay with my knobs in case I get annoyed by this setup. Make it slower, make it faster so that it works to my liking. And of course, the final touch is the obligatory poorly punched cover. Yeah, I messed that one up pretty badly. Every LED needs to be properly placarded, or else. And to boot, to make it look chic and classy, of course, the cover must be attached with slotted, not Phillips, press screws, which is very, very hard to do, apparently, when one of your hands is holding the camera up. Ugh. Do you want to watch me fumble through all four of them? Do you? Do you? Of course you don't. 2 is enough. Alright, well, that was it.